So I'd like to take a look at something that we've actually already seen on Lab 2, but we didn't actually take a look at the internals of quite yet, although some of you actually did on Lab 2, which is going to be a very good lead up into this next particular section that we're going to be taking a look at. That is an adder. So how do we take two binary numbers and add them together? First, a quick little review of how addition in binary works. It actually works just like it works with decimal values. So you take numbers, add them together, and then if you need to, you can carry a digit over into the next column. Now the big difference is here we only have zeros and ones, right? So at the most, we're only ever going to be carrying a 1, and we can only ever add ones and zeros together, which makes the available combinations actually pretty limited, which is going to make it easier for our circuits. So let's take a look at an example of an adder circuit and kind of take a quick look at how it works. So here is what's called a half adder, and I'll explain why it's called half adder a little bit later, but you can see that this truth table here is specifying two outputs. One is the carry out, so do I need to carry, right? And then the S column stands for the sum. And so the way that this works is we take a look at A and B, right? I add them together. 0 and 0 is going to be 0 in my sum column, and I have nothing to carry either, right? Because I didn't overflow the digit. We can take a look at the remaining values from the truth table, right? 0 plus 1 gives me a sum of 1, right? But I still don't have anything to carry out. It still fits neatly within the sum bit. Similarly, 1 plus 0 has a sum of 1 with no carry out. And then finally, as an example of when we need to carry, right? If I add 1 plus 1, we know that that's actually 2, but 2 can't be represented in binary. So what do we have to do? We put a 0 down for the sum, and then we carry that bit over to the next place. So that bit is now going to be carried into the next place of our binary digit. So you can conceive of a half adder as being a circuit that allows us to add two single bits together and produce a sum as well as a potential carry bit. So how does this circuit actually work? Well, you can construct the equations based off of this truth table, which is done for you right down here. Right, we see that the carry out bit is simply an AND gate. The sum bit is actually a little bit more interesting. Here it's represented as A naught and B, or A and B naught. However, if you're familiar with some of the logic gates that we've been talking about previously, you actually probably recognize that this entire segment here could be replaced with a single exclusive OR gate. So exclusive OR gates actually play a very important role in adder circuits. They can be used to compute sum bits. So this entire section over here of it's actually 5 gates if you count the inverters, could be replaced with a single exclusive OR gate. So a half adder works great for adding two bits together and producing the result. However, we want to add together larger binary values. We want to add binary values with 8 bits or 16 bits or 32 bits or even 64 bits. So we want to add a lot more bits to one another, which means that I need to have a way of incorporating a bit that's being carried in. So I consider the fact that this carry out bit exists. That carry out bit needs to get put into the next bit over, the next place over of my binary digit. And so far, this circuit that we've given, this half adder, has no way of accounting for anything that might be carried over from the previous addition that takes place. So there's a separate kind of circuit called a full adder, and you can see what it does is it simply adds an additional input. I still have A and B, which are the binary bits that I'm going to be adding. I have a carry out bit if I need it as an output. I have a sum bit if I need it as another output. But I have this new input called carry in, which is simply, do I have a carry bit from the previous addition, from the bit that's to my right, from the bit that's next door. So here is a truth table for this particular case. And again, I won't go through all of these cases, but I will point out a few of the more interesting ones, right? We can see again that if A is 1 and B is 1, we're going to produce a carry bit for our output with a sum of 0. we see that the carry in can now act as can now force a carry out bit as well. So if carry in is 1 and A is 1, then I will still have a carry output bit, and my sum will be 0. And now we have this interesting case down here at the bottom as well. If all three are 1s, so 1 plus 1 is 2, plus 1 is actually 3, so I now have a carry out bit, and my sum is also 1. You can see that represented in this particular case here, right? How that addition actually works. So this is the truth table now for being able to handle carry in bits as well as carry out bits for a full adder. And again, we can construct logic circuits, we can construct logic equations based off of this truth table, which you can see down here at the bottom. Again, notice that for the sum bit, in our half adder example, it was actually represented as a exclusive OR gate, or it could have been represented as an exclusive OR gate. And the same thing is true here. This is actually a 3-input exclusive OR gate. So everything that you see over here, right, including these inverters, as a matter of fact, could be replaced by a single 3-input exclusive OR gate. In fact, it would be replaced by such a gate in an actual logic circuit. And then for the carry out bit, you can see that the full equation is listed here on the top row, but there is some simplification that can take place that allows us to use fewer logic gates. I'm not going to go through that example now. You know enough about the properties of Boolean algebra to figure that out for yourself. So, we now have a full adder, which can be used for handling carry in bits as well as any bits that need to be carried out. But again, this is still only for 1 bit. We still only have we have 2 digits, right, added together, but it's only 1 bit that we're actually adding. So how can I extend this out? How can I create something that can add multiple bit numbers together? Well, that's going to be the last thing that I want to show you, which is called a carry ripple adder. So here I see a series of 4 full adders. These are 4 full adders in this carry ripple adder. And so you can see now that I've got 4 inputs, 1 for each bit of each value. So A is 1 binary number with 4 bits, and B is 1 binary number with 4 bits, and I want to add those together. So the way that this works is I take the carry out input of my binary value and I feed that into the carry in of the position that's next to me. You can see that's all changed together like so. I have an additional carry in, which typically would be set to 0, since when we're starting from scratch, there is nothing actually being carried in, although you could set it to 1 if you had a good reason to do so, right? And then for the output, you see I've got 4 bits of output down here that represents the sum, the result of my addition, as well as a carry out bit, which indicates whether or not I was able to fit my result within the 4 bits necessary. We'll talk about that a little bit more in the next video. So this is a 4-bit adder. You can see the block diagram for it here. If you ever wanted to use this in a circuit, this is perfectly acceptable to use. In fact, if you wanted to extend this to more bits, you could very easily just by changing the number 4 to be something else, 32 or 64, whatever the case may be. In fact, that implies that I would then have 32 full adders or 64 full adders or however many full adders I need to handle the different bits in this adder circuit. One final thing to note, we have recently talked about timings within digital circuits. One final thing to note about this carry ripple adder is the fact that there is some delay involved. So consider that I cannot get the proper answer for this bit here, S1, until I determine what the proper result is for this carry out bit from S0, since carry out determines, in part, what the value of S1 is. And the same thing is true of S2. I can't determine what S2 is until I determine what this carry out bit is of S1, but I can't determine what that carry out bit of S1 is until I determine what the carry out bit is of S0. And the same thing for S3, except for I now need to wait on all 3 of the previous ones before me. So one of the big issues with carry ripple adders is that it takes a little bit of time for those values to propagate. It's not going to be an instantaneous addition that takes place, and you need to be a little bit careful. I will actually see a result here relatively quickly. I'll see a result on the output right away, but that result will change as the carry out bits propagate through this carry ripple adder. And so this result will finally stabilize to the actual result once that propagation is complete. So this is actually a pretty big problem. Carry ripple adders are not used particularly often for this purpose. This is a problem that we need to address at some point, and we will actually address that in a future section.